Okay, so we're going to start off with sorting today. And particularly, we're going to be doing quadratic sorting because those are the easiest sorting algorithms to understand. So that's where we're going to start. The best runtime that you can get with these sorting algorithms, or with most sorting algorithms, is going to be what's called log linear, big O of n log n, and that's merge sort and quick sort. Merge sort uses a divide and conquer strategy. That's something, if you look at sorting algorithms, you'll definitely see. And then a more harder to understand one is quick sort, and quick sort uses less memory, but is still O of n log n on average, but n squared in the worst case, but pretty rare that you get a worst case. And there's definitely ways to mitigate that. So those are more complicated ones we won't be covering today. We'll be starting with the quadratic or the O of n squared sorting algorithms. Cool. So why sorting? Really just comes down to seeing the most relevant data first. This picture I think makes a lot of sense for you guys right now. On your e-commerce site, there's probably many different ways that you could be sorting the data. It's not to say that this is something you had to have, but hey, it's a cool feature. You can check out your items by price, by reviews, by number of reviews or newest arrivals. So all kinds of different properties on data. So on the consumer side, you want a good UX, right? You want to show the most relevant stuff first. So that's why sorting can be helpful with that. And on the algorithmic side, it can increase the efficiency of many operations. And that's going to be things like searching. If you've sorted data, you can do binary search. You can also do the ratcheting strategy that we saw. And that would be find two numbers that sum to X. If you're already sorted, you can use ratcheting. And then finding the mode. If you're already sorted, you can just use two index trackers as you walk through the array, and you can find the mode of the array. So sorted data, really good for the user experience, also really good for increasing algorithmic efficiency. And this is probably the extent to which we've done sorting so far. So with JavaScript and arrays in particular, we've got the dot sort method on arrays. And this is what's called an in-place sort. So the same array is sorted. We don't return a new array. The dot sort method does return an array, but it actually returns the same array that you called the method on.
Justin, are you
trying to share a screen?
Oh, yeah. Sorry. Let me roll back.
Thank you, sir.
Yep, sorry about that. So this is what we were just looking at, or what I was just looking at rather, when I was talking about why sorting. This is what I meant by something being very relevant to you guys. Is this little selector from Amazon where you've got the relevance, the prices, and some reviews and newest. So different ways to give the user the experience they're looking for by sorting your data and looking at different properties to order by on the data. And then these were the operations I was talking about. So binary search, finding the mode, finding two numbers that sum to X. We saw that in optimization with the ratcheting technique. And all of these require that you have some sorted data to operate on. And this is where we were just at. So the dot sort method, this is probably what we've been doing to sort so far. And it is in place, so the same array is sorted. You can also just return a whole new array and not sort the current array. If you were worried about mutating an array, you would just copy it into a new container with the ... spread syntax, then sort that array if you did not want the insort behavior. For large n, so for very large arrays, these are the time complexities we can assume, n log n time complexity, and O of n, so linear space complexity. And that's with Chrome and Node in particular. Some other browsers choose to implement different algorithms for sorting under the hood. Chrome, I believe this is for Chrome, they go with merge sort. So that's where we get that log linear time complexity and the linear space complexity under the hood. So we have to use a separate array. And then ordering. By default in JavaScript, elements are converted to strings and sorted in ascending order based on character codes. So sometimes that's fine if you're working on strings and you don't need to worry too much about how things are sorted. If you just need to know that the sorting is consistent, then going ahead and using default can be fine. But if we want to override default behavior, we have to pass what's called a comparator function. And here I've got an ascending comparator. So on line 8, left, we have the comparator, which is an arrow function, takes in two elements, often called left and right, and then we'll return left minus right. So what is this return logic right here? Takes two elements, will return a number from a comparator. If the return value is less than 0, then left comes before right. And if return value is greater than 0, then right comes before left. And if the value is equal to 0 exactly, then the two elements will stay in the same order that they were already in. So here we've got a few comparators. This one we are just sorting on numbers. So we're sorting that nums array and passing the ascending comparator to dot sort. And then here we've got people. So can't keep it so simple, but still pretty simple. We're just going to return l.age minus r.age, which is pretty simple sort, ascending order. But moving on from that, so doing our own, oh, there's an exercise, but we're skipping that. Moving on from that, we've got the big O of the quadratic sorting algorithms. Some are better than others. As you can see, a lot of it is big O of n squared. So we'll start with bubble sort, which is the probably easiest to implement sorting algorithm. And often not the best choice, but we do start there sometimes. We do start there just because it is the easiest to understand. So its time complexity is always going to be quadratic, and its space complexity is always going to be constant. Selection sort also going to have always going to have a quadratic time complexity, and we're always going to have a constant space complexity. The difference between bubble sort and selection sort is that although they have the same time complexity, selection sort actually does less swaps of elements in the array, and that's something we'll see. And then we have insertion sort. So as far as the quadratic category of sorting algorithms goes, insertion sort is the best because if it's already sorted, we'll only need to make one pass over the array. If you give bubble sort an array that's already sorted, it'll still be quadratic time, unfortunately. But with insertion sort, you get linear time at best, and in average and worst case, you get quadratic time and constant space. And these are the fundamental introductory sorting algorithms. The runtime of these sorting functions is based on the number of element comparisons. So these are often called comparison-based sorts as well. So to get beyond quadratic time, you have to what's called fix more than one inversion with each comparison. And that's something we could dive into later. So here's bubble sort. This is the most basic sorting algorithm we've got. We're going to bubble the i+1 largest element to the end of the unsorted portion of the array. So this comment here, we're going to gradually move the largest elements to the end of the array. We've got this outer loop, and notice we've got nested loops. So off the top of your head, you're thinking probably quadratic. We've got I starting at 0, and we're going to go to less than nums.length minus 1. And why do we have the minus 1? Well, we've got the minus 1 because we're going to have j in this inner loop, and we're going to go to j plus 1. So we don't want to index outside of the end of our array. So nums.length has to be the last element minus 1. So when we do the plus 1, we won't be going out of bounds and indexing something that isn't there. So, oops, excuse me. The outer loop, the one with I as its iterator, is going to essentially start at the beginning, and this is going to determine largest. So each iteration of the outer loop says, hey, we put the largest element at the end. Next iteration of the outer loop, we put the second to largest element at the end. Next iteration, third to largest element at the third to last spot in the array, rather. And then this inner loop starts at 0 as well, and we're going to go to nums.length minus 1. So if I is 0, we'll still just go to nums.length minus 1 again, so we don't index out of bounds. But once I has done one iteration, so I is 1, we'll also subtract I here. And that's because we've already found the biggest element in the array. So we don't need to worry about the last element in the array anymore because it's already correctly placed. Therefore, we can now worry about, say, the second largest element in the second to last index, or the third largest index or element in the third to last index. And then as far as the comparison goes in here, we just take the element at our current index, so nums index j, and we say if it's greater than the element to my right, you basically just go ahead and swap them. That's what's going on right here, is we store j plus 1 in a temporary, so the element to the right, put it in a temporary variable, and then at that index, put in j, since num's index j was greater than it. And then after we do that, num's index j becomes temp. And we have to store temp because we override j plus 1 right here. And if we didn't store temp, we would lose its value. So that's why we've got to put in a constant. So after we reassign to the right index, we still have the value to put in the left index if we are in fact doing a swap. In this process, we'll go ahead and bubble your largest value all the way to the top. So it'll be swap, 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 get it to the end. Then we'll start over second to largest, third to largest, so on and so forth until we're sorted. And this is kind of what I was talking about, this bullet point here, repeatedly swap elements until they are in ascending order. So lots of swaps going on here. And you can optimize it to have a linear runtime in the best case, but then you're not really dealing with bubble sort anymore. This is bubble sort. So if you were to go ahead and try to do a linear time optimization, then it's really not bubble sort anymore. It's a different sorting algorithm. And people love to hate on bubble sort. This is a big point, actually, maybe the most important one on the slide. If you get to an algorithm interview and someone asks you what algorithm you would use to sort something, do not say bubble sort, because a lot of people really don't like bubble sort just because it is always quadratic time. It has a huge amount of swaps. Almost anything is better than it. It doesn't matter if you've only got like 10, 20 elements. It's almost negligible. But once you scale your inputs up, which is the purpose of Big O, then this algorithm will get a lot slower than the others. So if you're ever in an algorithm to interview where you have to do sorting, avoid saying bubble sort. Say you won't use bubble sort. Almost anything would be better, really, such as selection sort, which is the next one. And this is an improvement. So we've got two subarrays in selection sort. We've got the sorted left and the unsorted right. So what we do is we find the smallest element in the unsorted subarray and place at end of sorted array. So we've got two portions of the array. We're just kind of theoretically partitioning it. This array nums in this case. We've got the sorted array, which is on the left, and then we've got the unsorted array, which is on the right. So what we'll do is find the smallest element in the unsorted subarray, so the right, and place at end of the sorted array. And once we've got it at the end of the sorted array, we'll move the I plus 1 smallest element to position I. So we're always just building up the smallest. So with bubble sort, we put the biggest element at the end. With selection sort, we want to put the smallest element at the front. And that's going to be the difference here. And we're going to use a variable to track the position of the smallest element in the sorted subarray. This will allow us to reduce the number of swaps that we're going to have to be doing. Swaps aren't free. We're still like moving data around in memory. So if we can just use a variable to track the index of the minimum value in the unsorted subarray, right here we've got min position filling that role, then we can reduce the number of swaps that we have to do. And we can only do one swap exactly at the end of each iteration of this outer loop I. So one swap for each outer loop iteration makes it better than a naive bubble sort because we've got the fewer swaps. So with this one, we're just doing numbers right here. If you wanted to expand to other data types, you would have to add a comparator. So a function that knows how to compare whatever type of data you're passing in, but we're just dealing with numbers. And this outer loop will start at index 0, and again, go to nums.length minus 1. That's pretty common in sorting algorithms, is not to go all the way to the end. In this case, if we're looking for the smallest element in the unsorted portion of the array for each iteration of the outer loop, when we get to the second to last element, we know we've already found all the smallest elements. Anything that is in the last position is by definition the biggest because we've been looking for smallest the whole time. So when we're looking for the second to largest, we'll put it in the second to last index, and we've got one value left, but since we've been looking for smallest, that's definitely going to be the biggest one. So in this outer loop, we'll start I off at 0, and we've got min position. So this is the variable to track the location of the smallest element in the unsorted portion of the subarray. And then in this inner loop, we're going to start j at I plus 1, and j is going to be less than nums.length, so j will go all the way to the end. And that's why we've got the -1 and the +1. So we could, in theory, go all the way to the end here. So if nums index j is less than nums minus position, so this is just going to iterate through the unsorted portion of the array, this loop here, and we're going to say, is the current element I'm looking at, is it less than the minimum element so far? And if it is, just update min position to be j. So I, wherever I is at, that marks the sorted portion. That index and everything to the left of it is sorted. J starts at I plus 1, so the unsorted portion of the array starts at I plus 1. And that's where the partitioning occurs. So the partitioning occurs on I. So I and everything to the left of it is assumed sorted. And then I plus 1 and everything to the right of it is assumed unsorted. So start off min position as index I, and then we'll go ahead and check out everything else here. Update min position, and then we will swap down here. So get the temp, and then we'll just go ahead and make that swap to get the smallest element and put it in its place. So this is an improvement on bubble sort, really just because we have a fewer number of swaps. The time complexity and space complexities are the same, quadratic time complexity and a constant space complexity, but we do get the improvement in our number of swaps, so that will save us some work. So if you are choosing between a bubble sort and selection sort, go for selection sort, definitely. And there is one more. We saw this on the chart, insertion sort, and this is your best bet, really. It's also going to maintain two subarrays, sorted on the left again and unsorted on the right. It's going to assume that elements to the left of I are sorted, and it's going to use J to iterate down into the sorted array and find the insertion point. And this should hopefully give us less swaps. As we kind of build up the sorted portion, we should be doing less and less swapping as we go along, because we are going to use variables to track again and only do our swaps at the end. So using J to iterate down into the sorted array, finding the insertion point for the current element that we're inspecting, and we have to move elements that are greater than current to the right. We iterate down into the sorted subarray, and we say, hey, it needs to go to index 5, and everything to the right of 5 needs to shift to the left, because we've got to vacate 5 because we've determined that that's where current should go. So you will be shifting some data in this method potentially. And the while loop allows for linear runtime in the best case. So if things are already sorted, we won't do any iteration in the inner loop, essentially. We'll just end up doing a comparison in the parentheses for the while loop. And this is the optimal quadratic sorting algorithm. So let's, excuse me, let's walk through this one. Take in the nums again, and we'll start I at 1. And I is going to be less than nums.length here. So we're assuming everything to the left of I is sorted. So we're assuming index 0, that's the sorted subarray. I and everything to the right of it is unsorted to begin with. That's the assumption here. And we're just going to look at the current element. So we're going to put that in a variable here, current nums index I. And we're just going to start J, our iterator for the inner loop, off at I. And if J is greater than or equal to 1, then we can proceed. If J is 0, then don't proceed, because we're going to index to J minus 1. So if J is 0, we would index out of bounds, right? And we don't want to be doing that. So it'll check here just to make sure we don't index out of bounds. And while J is greater than or equal to 1, and the element before where J started is greater than current, aka current is smaller than the element to its left, then we need to do a movement here. So nums index J is going to be the element to its left. So move the bigger element one to the right. And this is the data shifting that I was talking about. So just to walk through that again, I will start at the first position in the unsorted portion of the array, which is going to be index 1. We'll grab each element at I. We'll start J at I. Everything to the left of J is assumed sorted already. In this inner loop, we've got the J greater than or equal to 1, so we don't index out of bounds right here. And as long as we're at a valid index, we can go ahead and compare with the element before us. And if the element before us, nums j minus 1, is greater than current, then we need to swap. That's an inversion. Those are out of order. If the number to the left of me is greater than me, if we're doing an ascending order sort, which is the assumption here, then we've got to do some corrections. So what we do is we take the element to our left and we put it at the current position j, and then we decrement j. We decrement j because that's where the current element needs to be inserted at the end. And that's what we do down here. And the big takeaway here is that this while loop and this check right here, this nums j minus 1, so the element to my left is nums j minus 1. If the element to my left is not greater than me, then we're already sorted. So go ahead and just proceed. And that's the best case, which will get us the linear time, because we'll just have a constant time operations inside of the for loop if we are already sorted. So we can get linear time in the best case, and that's why you really want to try to use the insertion sort method for sorting. So just to recap all of that, lots of stuff. We got for small n, so for small arrays, roughly greater than or less than 20, roughly less than 20, quadratic sorting algorithms are fine. So for small data sizes, you really don't need to implement a more complex algorithm like a merge sort or quick sort. Probably overkill. It's probably doing more operations than it is worthwhile, than makes it worthwhile, rather. But for large input arrays, dot sort will be faster than any of the quadratic algorithms. And that's because it will be doing a log linear time complexity sorting algorithm. So for large n, opt for dot sort unless you want to implement your own merge sort or quick sort. And if you were interested in that, I would start with merge sort first. Merge sort is definitely, I think, the easier of the two when it comes to merge sort and quick sort. So definitely true in Chrome and Node that the larger the n, dot sort will be faster. They have pretty good sorting algorithms implementations, as you would expect, big companies and large platforms. And the larger n is, the more noticeable the difference will be. That goes back to essentially day one when we saw that graph with all the different functions plotted out on it, and you saw that quadratic increases way quicker than linear, and log linear increases a bit faster than linear. So insertion sort is the best quadratic sorting algorithm due to its linear runtime with already sorted data. And just hammering this in, lots of people hate bubble sort, especially lots of more like traditional computer science people really don't like bubble sort. So if you show up to an algorithms interview, don't do bubble sort unless that's all you can remember. If that's all you can remember, then I guess that's what you got to do. But really try to have selection sort and insertion sort down, and know that selection sort is better than bubble sort because selection sort does fewer comparisons, even though it has the same time complexity, and insertion sort is better than bubble sort and selection sort because insertion sort could be linear time in the best case if you already have sorted data. So that's the crash course on the quadratic sorting algorithms. You definitely aren't feeling like you should be able to implement these right now. That wasn't really the goal. It's kind of just to familiarize you with what's out there as far as sorting algorithms go. So in the future, when you dive into these, or if you're at a meetup maybe, and someone is asking you about sorting, you at least know some of the terms that they're throwing out there and have an idea of what's a good solution, what's not a good solution. Pretty similar to what we've been doing with ORMs. We're just trying to get some familiarity with sorting algorithms here. Cool. So any questions before we move on? Nope. All right. Okay, so we're going to go straight into group work because I think people still have a lot of work to do, and we're probably going to be taking up a lot of your time with code reviews. Those have been taken up